All right, this problem, it says find the reactions. Looks like the reactions are here at A and B, and this is the structure. So I encourage you, before you just dive in, to take a few minutes, not even minutes, a few seconds even, and just kind of see what you have. Well, I'm going to tell you right now, even though it doesn't look like it, we're going to assume A is a pin. And we're going to assume B is a pin. So if you try to draw a free body diagram for the whole structure, you're going to have two unknowns at A, you're going to have two unknowns at D, and how many equations are you going to have? Three. More unknowns than equations. You're going to have to take it apart somewhere. Where's a good place to take it apart? At B. Why? Because B is a pin, it has no moment. So you really could get three equations from a free body diagram of A, B, C, and then three more equations from B, D, and you would have 2 plus 2 plus 2 unknowns, 6 equations, 6 unknowns. So this is a determinate problem. Do we have to work it that way? No, because there's something else we should notice. I mentioned it as the last bullet on one of my slides to take advantage of, and I drew the weird snake to help you visualize it. Do you see any two-force members in this system?
Yes.
Yeah, BD is a two-force member. It's pinned on each end. It's not snake-shaped, obviously, but it could be. And so what does that mean? There are not two unknowns at D and two unknowns at B. There's only one. So that means if I look at a free body diagram of A, B, C, I have two unknowns at A, I have one unknown at B, because I know the direction. It's this angle right here. So to solve this problem, I just need to draw a free body diagram of ABC. See what a little thinking will get you? That's cool, isn't it? Let's do that. So I'm going to draw my free body diagram of ABC. So there's ABC. I'm first going to assume directions for A, AY, AX, and then here at B, I'm going to assume, I'm going to call that force B. It's not A, it has components in the X and Y direction. We may have to actually get those in a minute. And that angle is going to be 30 degrees. This is a right angle, so this is 60, so that should be 30. Is that right?
Yes.
Yeah. Now, how am I going to take this trapezoidal shaped load and apply that to my free body? Now, I know the area of a trapezoid, do you? Yeah, it's easy. You just average the heights and multiply it by the base. No problem. Where's the centroid of a trapezoid? Off the top of my head, I don't know that one. So I'm going to suggest to break it down into things that you do know. You do know a rectangle and a triangle. So looking at the rectangular section first, what is the area of the rectangular portion? Well, the total length, or the total base is 9 meters, and the height is 2. So that's going to be a force of 18. So I'll draw that one first. So that's going to be 18 kilonewtons. And it's going to act in the middle. So half of 9 is 4.5. I'll just write that to this side for right now. And what I'll do to help you maybe see it better, I'll use a different color for the triangular part. And what's the area of that triangular section? Now, a common mistake is to come over here and look at this total height here and say, oh, the height of the triangle is 4. But it's not. What is the height of the triangle? Well, I've just taken off the 2 for the rectangle, so the height here is only 2. So I'll emphasize that. So remember, the area of a triangle is 1/2 the base, which in our case is 9 meters, times the height, which is only 2 kilonewtons per meter. The 2's cancel and you get 9. Is that good? Everybody see that? So I'll come down and put that where I think the centroid's going to be. Oh, by the way, where is the centroid of the triangle?
1/3.
It's 1/3 from the tall side. So 1/3 of 9 is 3, so that would be 3 meters from this edge. And we'll see what else we need to make it work in a second. So I think that's got everything. Oh, I forgot to label it. Free body diagram. There you go. Now you remember what it is. So what should we do first? Should we sum forces in the x direction? No. Why? Because I have an unknown x here and I have an unknown x component of b. How about sum forces in the y? Same. One unknown here, one unknown here. Can't do that. So what are we left with? Summing moments. About where?
A.
You could do A, and oddly enough, you could do it about B. Either way, you would create one equation and one unknown. But I'm going to do A because I like to always sum my moments about the pin. So let's do that. So I'm going to come over here, and again, sum moments. It's going to assume right-hand rule for my sign convention. We're going to sum moments about A and make sure it's in equilibrium. So what creates moment about A? Well, I have my B reaction and a couple of unknowns. Now, when you have a force like this at an angle, I find it easier to break it down into a component that is line of action is perpendicular through the point. That would be the x component of B. See, it's going to pass through A, so it's not going to create any moment. Right? But we're going to have the what? The y component of B. This piece right here. And what is the y component of B? Well, it would be B times the sine of 30. So now when I sum moments about A, I'll have this force here, really easy to find the perpendicular distance, and then I'll have all these. So I should be able to solve for B. So starting with that, this component of B creates positive or negative moment about A with right-hand rule. It's going up.
Positive.
It's going to be positive. So I'm going to have a positive moment created by the force B sine 30. And what's the distance from here to here? 6. Now, I'm going to take each of these forces about A. We'll start with the triangular force. Well, actually, both these forces are going to create what kind of moment about A? Positive or negative? Negative. So we'll start with the... Oh, I just noticed I forgot to put my 9 kilonewtons there. Sorry about that. So the force would be 9 kilonewtons. And what's the distance from A to the centroid? We mark that. It's 3. Then I have another negative moment with the 18 kilonewton force. And what's its distance from A? Well, remember, it was halfway, so that would be 4.5 feet, right? Because the total distance was 9, halfway would be 4.5. So it's going to be 4.5, and that's meters. So we just need to solve for B. Somebody solve for B. I'm not very good at doing trigonometric functions in my head. Sorry, what?
36 kilonewtons.
Exactly? Wow. 36. And it came out positive, so I assume the right direction. That kind of makes sense, too. With all this load being gravity-based and trying to rotate ABC down clockwise, you need something to push back in the opposite direction. So that makes sense. If you had a negative value there, then you would probably want to think something's not right. This link doesn't need to be pulling down that structure to keep it in equilibrium. It needs to be pushing it up. So don't forget to check those things. All right, now let's get our AX and AY. Which one do you want to do first? Sum forces X or Y? Let's vote. We're a democracy. Everyone who wants to sum forces in X, raise your right hand. Nobody. Great. So we just want to do Y. Way to participate. Just like in a regular election. That's right. Were you guys eligible to vote in 16?
Nope.
Yes.
Nope.
Was anybody here eligible to vote in 16? Did you?
Yes.
Was not
Good for
eligible.
you. Good
Was
for you.
not.
Good for you.
Wasn't eligible. But it's okay.
Good for you.
Turn up.
Traditionally, your demographic has chosen not to participate.
They still got opinion.
That's right. Don't let the old people rule the world. Get out there and vote. It's your world now. Fix it. We broke it. You can fix it. Right? Because you didn't break it. You just got it, right? It just got handed to you. Fix it. Clean up all that plastic. Get it out of the oceans. Get it out of my water. Okay, enough of that. All right, so what are we going to do? We're going to sum forces in the y direction. So we got AY acting up. Which part of B is acting up? Oh, it's the same one I just had, right? So I'll say plus B sine 30. Those are my reactions. And what's acting down? Anything? Well, my two forces, right? 9 kilonewtons and 18. Now we know B, so we can plug that in there. So the only unknown should be AY. What's that? I sense it's going to be very small. I don't know why. Well, it's relatively small.
It's 9.
9? Anybody else get 9? Is it exactly 9?
Yep. 9.0.
Times 36.
Anybody else? I got 2.
Times
3? Okay, cool. Positive? Excellent. And then last, we're going to sum forces in the x direction. This is not a trivial one because we got some work to do here. So we've got AY acting to the right. Is that positive or negative? That's positive. And now we've got BX. It's going to be hard for me to draw it in there. I'll try to just put it in there a little bit. It's going like that. So it's to the right. Everybody see that? Kind of hard to see. So that's going to be positive or negative? Positive. And that will be the cosine of the angle. Again, we know B, so we can put that in there. So we should be able to solve for AX. So what is AX? Negative 31.2. Anybody else get that?
Yes.
Excellent. So that means that the reaction at A is not pushing to create equilibrium. It's having to go to the left. It's having to pull back. And that makes sense too. Your structure really, without this bar, is trying to rotate down and pull away from the wall. So the wall's got to pull back. So again, I think those make some sense. So any other questions about that? Great.